Every single atom of iron in your blood was forged inside a dying star. The calcium in your bones, the oxygen filling your lungs right now, all of it was manufactured in a stellar furnace billions of years ago and blasted across the galaxy in a catastrophic explosion. You are, quite literally, the aftermath of a star's death. But here's what nobody tells you. That death, one of the most violent events in the known universe, unfolds in a sequence so precise, so mechanical, and so terrifyingly fast that the star itself never sees it coming. Today, we're going inside the final 24 hours of a star, and by the end, you will never look at the night sky the same way again. To understand how a star dies, you first need to understand what keeps it alive. A star is essentially a war, a constant, violent tug-of-war between two opposing forces. On one side, gravity, pulling every atom inward with crushing, relentless force. On the other side, nuclear fusion, the process of smashing hydrogen atoms together at 15 million degrees Celsius to create helium, releasing an almost incomprehensible amount of energy, enough to push outward and hold the star up. Our own sun converts 600 million tons of hydrogen into helium every single second. Every single second. And it's been doing that for 4.6 billion years. But here's the brutal truth, that hydrogen supply is not infinite. And the moment it starts running out, the clock starts ticking. For a massive star, one at least 8 times the size of our sun, the beginning of the end starts subtly. As hydrogen in the core runs low, gravity wins a small battle, and the core contracts, heating up even further. This heat ignites helium fusion, then carbon, then oxygen, neon, silicon, each fuel burning faster and faster in a desperate cascade. Hydrogen fusion takes millions of years. Helium, a few 100,000. Carbon, about 1,000 years. Neon burns out in just 1 year. Oxygen, a few months. Silicon, the last viable fuel, burns for exactly 1 week. 1 week. After billions of years of stable burning, this star is now racing through its remaining fuel like a bonfire consuming its last logs. The star has entered what astronomers call the onion shell phase, and it is beautiful, terrifying, and completely doomed. And then comes the poison. Iron. After silicon burns out, the core fills with iron, and iron is where nuclear physics draws a hard line. Every element up to iron releases energy when you fuse it. But iron is different. Iron absorbs energy instead of releasing it. Fusing iron doesn't power a star, it drains it. So when that iron core builds up, fusion simply stops. No more outward pressure. No more war. Gravity wins, completely and instantly. The iron core, which has grown to roughly 1.4 times the mass of our entire sun, compressed into a sphere just 20 kilometers wide, suddenly has nothing holding it up. In this moment, the star has approximately 1 second left to exist in any recognizable form. 60 years from now, when the light from this explosion finally reaches a distant telescope, astronomers will look back at their archive images and notice the star was simply gone. What happens next is the most violent event in the universe short of the Big Bang itself, and it unfolds in 46 milliseconds. That's less time than it takes to blink. The iron core, roughly the size of Earth's moon but containing more mass than our sun, collapses inward at 70,000 kilometers per second, about 23% the speed of light. In that fraction of a second, the core's density becomes so extreme that electrons and protons are forced to merge, creating a tsunami of subatomic particles called neutrinos. And here's where physics does something extraordinary. The inner core becomes so dense, 100 trillion times denser than water, that it goes rigid. It literally bounces. That bounce sends a shockwave ripping outward through the star at 30,000 kilometers per second. The shockwave hits the outer layers and detonates the entire star in what we call a core collapse supernova. The numbers from a supernova are so extreme, they break human intuition. In the first 10 seconds, a supernova releases more energy than our sun will emit over its entire 10 billion year lifetime. At its peak brightness, a single supernova can outshine its entire host galaxy, all 200 to 400 billion stars combined. If one happened just 50 light years from Earth, the radiation would strip away our ozone layer and trigger a mass extinction event. The closest candidate star for a supernova? Betelgeuse, a red supergiant sitting 700 light-years away, already showing signs of irregular dimming and instability. When it explodes, and it will be visible in broad daylight for weeks. Humans alive today may actually witness it. You might be one of them. But the explosion is only half the story. What's left behind is even more astonishing. If the original star was between 8 and 20 solar masses, the collapsed core survives as a neutron star, an object so dense that a single teaspoon of its material weighs 10 billion tons. Neutron stars can spin up to 716 times per second, emitting lighthouse beams of radio waves so precise that scientists initially thought they had detected alien signals. They're called pulsars, and some neutron stars have magnetic fields 1 trillion times stronger than Earth's, so powerful that if one passed within 1,000 kilometers of you, it would rearrange the atoms in your body before you could feel anything. But if the original star was massive enough, over 25 solar masses, not even neutron degeneracy pressure can hold back gravity. The core keeps collapsing into a singularity, into a black hole. Here's the twist that changes everything. The supernova explosion doesn't just destroy, it creates. The shockwave blasting outward through the star generates temperatures so extreme that it forges dozens of new elements on contact: gold, platinum, uranium, iridium, elements that could never be made by normal fusion. These elements get scattered across light years of space as a glowing nebula, a cosmic cloud of raw material drifting through the galaxy. Over millions of years, gravity slowly pulls that cloud back together. It collapses into a new solar system. A new star ignites at the center. Rocky planets form from the debris. And on at least one of those planets, possibly many more, those scattered atoms of carbon, nitrogen, oxygen, and iron assemble themselves into oceans, into continents, into cells, into life, into you. You are not just made of stardust. You are a star, recycled. Every second, somewhere in the observable universe, a star is dying this exact death. In our galaxy alone, a supernova occurs roughly every 50 years. The last one visible to the naked eye from Earth happened in 1987, supernova 1987A, and astronomers are still studying its expanding shockwave today. Right now, there are stars running on their last weeks of silicon fuel, cores collapsing at a fraction of the speed of light, shockwaves tearing through ancient stellar bodies while you sit here watching this video. The universe is not a peaceful place. It is a churning, exploding, endlessly creative engine, and death is its most powerful tool for building something new. The atoms that will form the next Earth, the next ocean, the next form of life, they're being forged and scattered right now, in the last 24 hours of a dying star. If you found this mind-blowing, subscribe for more videos like this every single week. The universe has a lot more secrets left to reveal.